Okay, let me steal 2 minutes just to advertise a little bit of the org that I work for. So AI for Science is an international organization under Microsoft Research. So we are a research institute. We have 3 offices in Europe, Cambridge, UK, Amsterdam, and Berlin. So yes, Microsoft do work on science. We have a wide range of topics from crystal generation to DFT functional. So this one is a later work that just announced recently, Scala, and also to protein structure prediction, bioemail. And you can find out a lot of our research news and on our official website here. And most importantly, we are actually hiring. So we have full-time position opening. There may be more job advertisement online in the coming weeks. So please look at Microsoft Research Career if you're interested. And we also recruit interns all year round, but that advertisement do come up more sporadically. So just check it. Usually we have it before New Year's, but you can also just talk to me during the break. I think it should be very easy to catch me. I'm here till Sunday. Okay, so let's get back to the talk. Maybe before I start, put a little bit liability statement here. My PhD training is more on material science. I spend a lot of time doing case study, where I work with experimentalists to figure out, oh, if you see this material, something wrong, what could be the underlying cause, and I only work on a series of material. Only during my postdoc time, I starting to work on machine learning. So maybe my contact with machine learning will be just as long as with some of you. So please feel free to challenge me or raise questions during the talk. I have way too many content. I don't think I can finish before lunch. So ask questions, okay? Yep. So let me start with survey. Everyone knows shedding a cat, right? How many people know Maxwell demon? Raise your hand. Okay, half. How many people know this one, Laplace demon? 1. Yes, I know you guys don't know it. So this is Wikipedia definition. Laplace demon was, of course, proposed by Laplace back to the early 19th century. This is a demon that they say, oh, if you know classical mechanics and you know the particle, every single particle in the universe, then we should be able to master the whole world to predict what will happen in the next second, even to next 100 years, because everything should follow Newton's second law. Of course, the Laplace demon is not that realistic. It was proposed in early 19th century. In 20th century, statistical mechanics and quantum mechanics already denied the possibility of the existence of such demon. But the Laplace demon, or we actually still have a lot of practitioners on Laplace demon these days, is called molecular dynamics. Molecular dynamics, at least the classical molecular dynamics, is exactly doing the things that if I know Newton's second law, if I know exactly, how two atoms or how electrons interact with each other, I know the energy, I can derive the forces, then I know the acceleration, and I can move the atom. If you can move 10 atoms for 1 femtosecond, maybe you can move 100, 1,000, a million, or a billion atoms, all the way from femtosecond to seconds, or hours, or year, right? So this is kind of the idea of molecular dynamic simulation. But just to give you a little bit sense of how ambitious this is, look into the scale of different kind of reactions or behavior inside materials or real world. When we talk about chemical reactions, it's usually sub-angstrom. It happens, the reaction itself, like when there's bond breaking, happen very swiftly under femtosecond. And if we look into fast ion diffusion, so for example, if you have a piece of lithium battery or a fuel cell, like the atom is literally moving in the lattice, it happens usually like a couple hundred times or 1,000 times within nanoseconds. So that's 10 to minus 9. And we talk about lattice. Lattice is around 1 angstrom to 3 angstrom or 5 angstrom, that level. And if you're looking into, oh, I have a piece of surface, there's something changing on the surface, like, for example, let me think, you have a piece of catalyst, it could degrade over time, and that kind of movement, long-range movement to change the surface, usually the time scale and length scale we're talking about is already entering 100 nanometer to micrometer and, length scale, and the time scale will already go to second or microsecond. And there's worse things, right? Things could crack or go all the way up to the actual device, the piece of battery and protein. So here in total, we're talking about around 10 to 12 order 10 to 12 difference in the length scale, and also another 10 to 15 or even 10 to 20 difference in the time scale. So indeed, even just try to be having these Laplace demons is pretty ambitious. As I said, right, quantum mechanics and statistic mechanics will tell you it's impossible to have Laplace demon, even if you manage to run the molecular dynamics in the real world scale, it's impossible, because quantum mechanics will tell you you can't measure things very precisely when you go to a very, very small scale. And statistical mechanics will also tell you there's thermodynamics, you have increased entropy, you won't be able to predict things very precisely. But even if you're using those kind of methods, like for example, most of the generative model these days are assuming that things are following the Boltzmann distribution, or transition state theory, if you care about the kinetic rate of things, then even in this method, there's something behind that is the energy. So you still need to know the energy function to know the real world, even if molecular dynamics, the assumption may not work very well. So if you're a computational chemist, you may work with energy function a lot. They're actually so desperate at some point that they go to religion to make an analog to what they're trying. They call this Jacob's ladder. So basically, if you search on Google or anything, you'll find these Jacob's ladder with different methods. So basically, the chemists find out many different approximations to solve the Schrödinger-Dirac equation. And the rougher your approximation, the cheaper it is, but then it's further away from the reality. And of course, you can go to the exact solution, which they believe is the heaven. It will be very expensive, but it modeled the Mother Nature very well, right? Yeah, just here is a side note. Only after moving to UK, I know not everyone wants to go to the heaven. If you go to the Bath Cathedral, they literally make the Jacob's ladder outside the church, and there's some angel that is trying very hard to leave the heaven and come down. Okay, so again, let's plot the Jacob's ladder in a slightly different way. If you ask a computational material sciences or physicists, they would rather make their energy model plot in this kind of way to plot their capability in time scale and length scale. And it depends on different kind of approximation. So the so-called first principle is the things that usually you will consider the behavior of electron. This is very expensive method that usually scale n3 to n5 towards the number of electrons in the system. And that's why to date, this kind of system, you can either model a slightly larger system, but then you cannot afford so many calculations. The time scale you can model is very small. And if you want to model longer time, you have to go to very small system. There is another approximation. This is the classical force field, where we say, most of the mass of the material is actually centralized on the nuclei. Why do I care about electron? Let's cross-grain all of them away and only care about the nuclear movement. And in that case, we can simplify the algorithm towards depending to the number of atoms. And in this case, also because you throw away all the electrons, many of the solving the Schrödinger equation, many of the degree of freedom is already gone. It's a much lightweight method, so you can get much faster. You can calculate way more length scale to time scale. And then also the dependency, you can see the slope is much shallower. However, these kind of methods do not come with no cost. Oh, give me a sec. So most of the energy model that we are using these days, they always face this GAS trilemma, meaning generalization, accuracy, and speed. So for first principle method, because most of them are explicitly solving electrons, they're very general. You can apply the method to any elements that you like transition metal, heavy atom, no problem using it. But they're very slow, so they're very slow on the speed. They're very accurate. While classical force field, because they throw away all the electrons, they are really, really fast. I will explain later, but they do way too much approximation that usually every single classical force field only work for one single system. So you use this force field, it can only apply to this element, and they don't have any generalizability and accuracy. Machine learning force field is something trying to compromise between the two, that they try to bring up the generalization as much as the first principle is. But of course, because the functional getting more complicated, we're using modern machine learning architecture. They're way much slower than the classical force field. Sometimes people will ask, why do you care about the JS trilemma? So if you actually ask before 2022, people will say you are generating a new problem that people don't care about to solve a JS trilemma. Because many people who only care about materials or who only care about protein, they do their simulation using the method that was invented back to 80s or 90s. Nobody cared about generalization or accuracy. But it is not true. If you look into most of the literature, nobody cares about all these important systems that include systems that between domains. So for example, enzyme system or zinc finger, this one have a metal core and protein. So I'm a materials person, so please correct me if I make anything wrong, state anything wrong on the chemistry and the biology side. And you can also have MOF, metal organic framework, where you literally mix a little bit organic molecule together with metal. Or interfacial system, heterogeneous catalysis have organic molecule on top of metal. And of course, if you look into, there's a lot of reactive chemistry. These are all the systems that is actually super important for the industrial application and consumer application. And people are not modeling them at all, because an energy model that can solve the JS trilemma has not existed. Sorry, I still need to learn the pointer. Yeah, so let's go a little bit into the technicality. I do struggle a little bit whether I should tell the story first or I should throw the equation first. But I figure out that most of you here are actually very, very advanced in machine learning. So let's go through the equations and stop me if you have any question, but so that we are on the same common ground. Because machine learning force field is quite different from a generative model. So go back to the definition. Machine learning force field is a regression model where you know the position of atom X, that's your input, the n by 3 matrix, and an n by 1 matrix that describe the pseudo-atom, like either it's amino acid or it's an atom element. And your output is just a single scalar. And from the energy, you can take a gradient to get the forces. That's it. Of course, some people would do it separately. They may directly predict forces. Most of these models are trained on DFT, so ab initio method, where they explicitly calculate the electrons. In force field, we don't have any position for, don't have any description on the electrons, right? So they would take the label coming from this higher order method, which do exactly the same thing. Input X, output Y. You just do an MSE loss or Hilbert loss, train the model, done. So it sounds like a much easy task than a generative model. There's no diffusion process, there's no noise injection, right? But it's very different from a generative task in 3 aspects. First is data. When we're talking about a generative model, we're actually talking about, we try to sample the real world with an assuming probability distribution, right? And this probability distribution may control by the energy. So that determine most of the data that you guys get, either from experiment or from molecular dynamics that using a force field to generate. The data itself is all at the low energy part of the whole potential energy surface. They are high probability configuration. But force field do not care about the probability distribution. We care about the things on the exponent. And therefore, in the force field data, we have way more dirty things that is high up in the potential landscape. And most of the time, it's actually critically important to have this high energy or messy data to make a force field good, to guard your force field, to do some stupid things. And the reason is, force field have a very different accuracy requirement. A generative model, you may say, I have 90% of the structure that is predicted correct or match have a low RMSE. You're treating the 90% good one and the 10% bad one kind of separately. But in force field, it's not the case. In force field is, we need to be good in the whole continuum phase space. And if you are wrong in a tiny corner in the phase space, and when you run the MD simulation and somehow accidentally encounter that tiny wrong space, boom, everything exploded because of the butterfly effect. The error in that tiny corner may accumulate and explode over your integration of molecular dynamics, and your whole simulation in the end will be very bad. So in terms of accuracy criteria, force field is way more strict than a generative model. And in the end, the speed and scaling requirement is very different. So maybe you guys can tell me, what is the typical size of pseudoparticle or amino acid of the generative model that you are handling day to day? 100 atoms? Can anyone raise hand? 100? 1,000? OK, anyone go to 10,000? 10,000 is the minimum criteria for force field. And then how many samples can you do per day? 10,000, maybe? 10,000? Yeah. But 1 million steps is the minimum criteria per day for force field. So we're really talking about very, very different things here. I think it's very good to have a discussion here, because the previous days I heard a lot of students asking, oh, whether equivariance is important. Maybe rethink a little bit on how people come up with your generative model. They borrow a lot of things from force field, because force field was the first machine learning task, like from a long time ago. You'll see the history story. But we have a reason to do things, because we have very, very specific criteria. You may not suffer from the same criteria. Right. So when you search a machine learning force field paper, you may encounter a zoo of many different architecture, like things look at these boxes. And if you're coming from the computational community, read the literature a little bit before 2000, you may also see a zoo of selections of force field with simple equations. They all look different. Why that's the case? Let's go back to step 0. I know some of you never work on deep geometric learning, right? So maybe pay a little bit attention. This is actually the typical interview questions that I will pull out if we're interviewing a researcher at Microsoft, because we like to throw people to the ground that they're not familiar with and see whether they can navigate with their intuition. So step 0, I ask, if you have an n by 3 matrix and an n by 1 matrix as the input, output is x. How will you design your architecture? The first constraint I will ask is, how do you preserve the permutation invariant? If I have a molecule that is HCH3, it's no difference from CH4. What are you going to do? You can't just, I concatenate everything as slab and MLP. It doesn't work. So to preserve the permutation invariant, you can only do a couple operations, right? Multiplication, summation, through the whole thing. That's the only thing that you are allowed to do. Of course, you can do a little bit sophisticated. You can get your getter global information, stack it back to local. Step 1. Step 2, of course, immediately, I will tell you the point cloud itself, every single atom has a position in the 3D coordinates. How do you preserve the rotational and permutation invariant? Most of the time, actually, people coming from outside of our community, their first answer is, just subtract with the center of mass. What's the matter? After you do an alignment and data augmentation, you will get everything. It's actually not bad. I do see people doing that until 2022. To my surprise, they can get the MAE on like things like open catalyst data set very, very low if you don't really use it for an MD simulation. So yeah, think about that again. But of course, a classical solution, or most of us will intuitively think that, let me just transform it into a graph and look into the distance matrix so that I turn the n by 3 matrix, immediately blow it up to n squared by 3 matrix, and times a 3-dimension, right? The atomic number of, well, the distance, Rij, the atomic number of one end and the atomic number of the other end. Then from here on, I solve all the invariant problem, and then I can use whatever MLP. And this is actually very similar to what we usually call a two-body descriptor, where you just decompose the whole system into many pairs and only look into the pair. But it immediately encounter a problem here. So most of you are probably working on protein and molecule, where n squared is probably acceptable. But for people working on crystal, there's no such thing called full graph. Because in crystal, we have periodic boundary. So every single atom is replicated through the periodic boundary. You connect to the image. And then even though in the non-periodic boundary, we say, oh, the number of the matrix size is just n squared. But in PBC, the matrix goes to infinity. You can't just use simple distance matrix to work on it. Of course, a straightforward solution is just apply a threshold, and then you do a cutoff. Say, I throw away all the edges that is longer than certain distance. Then immediately, you reduce your dimensionality from n squared to n times m. You get back to the linear region. So this is, yeah, OK. But once you apply a cutoff, you lose a lot of information. Originally, we come from n to n squared and down to n times m. But it's very dangerous, right? So for example, if you only look into pairwise distance, you cannot tell that these two configurations are different because the distances are all the same. And some of the long edges are already thrown away, so you don't know them. If you have a full graph, you can still infer the information from, for example, these connection, right? But now I only allow the limited 4 edges. You can't tell. And that's why people have to introduce some many-body information to complement the information loss that we have done by thresholding the configuration, thresholding the distance. Some people can do it very explicitly, just doing torsion angle, or like angles between edges or angles between 4-body. There's a many classical way to describe how 3-atom object or 4-atom object, even all the way to 5-atom object, how different they are. And this is basically what people do until about 2000. And until this step is still in the classical force field regime. So now I think we're a little bit more ready in the equation part. Let's jump back to the history. The first force field, I have no guarantee. This is so far I can find. One of the paper at 1931, when people are trying to work on van der Waals interactions, they already have some analytical equations in presenting how the two molecules should interact with each other with a simple equation. And what they have done at that time is actually approximate the Schrödinger equation. Of course, computer at that time probably still in the wartime lab there. They're just solving everything manually, and they approximate the equation manually. All the way until 1970s, most of these kind of work are very, very theoretical. In 1970s, people can already starting to do some force field research on computer. It limit to about 10 to 50 atoms. But at that time, they already have most of the formalism that you see these days on classical force field. So here's an example. They are trying to model uranium dioxide, 1977. Maybe most of us would never touch uranium dioxide in our life, but the crystal structure of uranium dioxide is actually not that unfamiliar to you. If you see fake diamond before, it's zirconium oxide. They're the same kind of crystal structure as uranium dioxide. The only difference is uranium is a crazy element. The valence of uranium can range from +1 to +6. But it's so important, and you want to know how they behave in a nuclear reactor. So people have to model it. And what they come up with is this equation. Let's say I only care about the pairwise interaction. Each atom, it comes with a charge. So this is the charge of the uranium. They treat it as a 4+. And then they plug in the equation. Let's say 1, 2 is the uranium and the oxygen interaction. They have only 3 parameters for this force field. And there's also some spring constant. So they also add here is a so-called Korschelt model. So every single atom is split into 2 parts. One part carry most of the mass, the other part carry most of the charge. So then they can breathe a little bit and kind of simulate the dielectric behavior of the ion. So this is very, very crude formula, right? Only how many parameters we have? About 10 parameters for the whole materials. And the fitting of these 10 parameters is actually a little bit dark art. If you are trying to do it today, I'm not sure you would do it correct because atom optimizer wouldn't work on this. Most of the parameters is scaling very different. Some is perfector, some is exponential. And they directly fit it to experimental value. So what they do is, I have this force field, I throw it into an emulator or optimizer to see whether I can directly predict an experimental quantity. And if I see something wrong, I go back to adjust the parameter. So you need to use a lot of black box method, black box optimizer on that. It's actually a dark art. Back to 2000, There are not that many groups that is doing force field fitting because not everyone know how to do the parameterization of these equations. Yeah, but they do have a little bit first principle things. So one of the subset of the parameters are fitted from ab initio. So the oxygen-oxygen interaction, they do DFT, Hartree-Fock calculation, because it's two atoms, is totally affordable back to 1970s. They just literally these two oxygen, 2.2 that was born difference, and then just stretch it away, and then you get some number here. Then you do a fitting on the equation. Just note that this error is horrible. I mean, on today's standard, maybe none of us will be able to graduate with this number, right? But this is a magic number somehow. Even till 2015, people are still using this group of magic number. Not only in uranium dioxide, it somehow magically works on almost all oxides. And the funny part is, in most of the oxide, oxygen is 2 minus. But what they're modeling here is oxygen minus. Not oxygen, not isolated oxygen, not neutral, oxygen minus. And this works. So it's kind of a lesson for us to know, like, this is the power of prior knowledge. If you know something, you can really easily circumvent a lot of data problem. But what I show you is only for uranium dioxide. So back to 80s, 90s, they immediately starting to realize that I cannot use one single functional to fit all the material. Why? Because there's a huge division between world. In organic system, we're talking about a bond length of 0.7 angstrom to 1.5 angstrom. CH bond, HH bond, they're very short. And most of them, maximum 6 neighbor. I actually haven't seen a 6 neighbor. Maybe chemists can correct me. The carbon is sp2, sp3, hence 2 or 3 neighbors. But in organic system, if you look into a metal, so we have this so-called FCC, BCC, so it's different kind of close-packed stacking. The atoms are way much larger because they're heavy atom. Here, we're talking about most of the atomic numbers under 20. In solid state, we're talking about atomic number from 20 all the way to 100. The element is very heavy, the radii is very large, the bond distance is 2 to 3 times larger. 3.2 angstrom, and the number of neighbors, of course, is way much larger. In a close packing, you have 12 neighbors, so just think of the ball, they stack together, just play the hard sphere game yourself. If there's some defects, it can go up to 14 neighbors. So we're talking with very different number here, and people immediately say, well, since they're so different, why don't you just use different equations to fit them? And that's where the world is starting to divide. In the organic world, people use a lot of just harmonic, let's say 2 things are bound together, you use a spring, or you use something like a Lennard-Jones potential, just look into each pair. But in the metal world, in the solid state world, people like a lot of things that involve density or many-body interaction. Then they will say, oh, my functional will be a function of density. It has very different consequence. The upper equation, your energy will scale with the number of edges. In the lower equation, your number will not scale with the number of edges, but normalize with 4 pi r squared. Is actually, you can also see the difference from looking into the macroscopic and microscopic difference of these kind of materials. Organic materials and gas phase, the density is usually no more than 2 grams per centimeter cube. While in inorganic system, we're talking about 5 to 20 grams centimeter cube density. And when you look into the radial distribution, in crystal, everything is very regulated pattern, right? So you will always see a spike in terms of which shell that they locate. And this spike will actually never go down, no matter how far you go. They always will have places where the value will go to strict 0. But if you look into organic system, they may have 1 or 2 spike. For liquid, it will just converge to 1. If you have a gas phase or non-periodic boundary, at the end, the density of your neighbor will go to 0 because far out is vacuum, there's nothing. So they're very different. In solid state, you really need to take care of, when you go far out, things need to be normalized. You can't afford the edges to explode to infinity. There are also people trying to do a little bit like what we are doing these days. They're really, before their time, they're doing first principle optimization. The only difference is they are not using anything like a modern optimizer as we do. The number of parameters they live with is also very little. Yeah, that's just a side note. So a recap, basically, before 2000 or even before 2010, people were extensively using this kind of classical force field to describe the materials. The number of parameters is no more than 100, so 100 is basically react-FF. That was the only force field that can do a little bit reaction back to that time. And even at 2012, when I was taking molecular dynamic classes, our teacher was ranting about react-FF, saying that, how could you have 100 parameters? Any of your fitting will go wrong. 10 and 20 parameters should be enough. Never go that much. It was very funny, but they do achieve a lot. So given any phase that observe experimentally, they can give you a parameter that pretty much produce experimental observation. You can still visit this kind of database, OpenKIM, to see most of the data that they collect, or a force field parameter that they collect for different elements, how they compare with the experimental method. They already have most of the things that people are talking about, long-range interaction, far field charge optimization, reactive force field. They are also a very open community. Many of the software that people are using these days are started around 1990s, and there's still a lot of active developers. These are amazing people that will merge your pull requests at Saturday night, 12 a.m. But of course, as we said, right, there's a reason that they are no longer popular these days, because they do fail a lot. Back to our example of uranium dioxide. Uranium is crazy. It can go from 1 plus to 6 plus. The force field that I showed you before would immediately not work if you have all different kind of uranium. It was actually critical failure for them, because uranium dioxide, when you use in a reactor, it will get radiated by high energy neutron that create a lot of different defects. Once they get irregularity, they could have different valence states. It's like, basically, once the symmetry breaks, things are not that easy. The simple functional would no longer work. They don't have that much expressivity, of course, because it's a simple equation, and they also have no statistical analysis on its performance. So for example, react-FF is already very close to what today people are talking about on machine learning force field. They're able to do a lot of reaction, but then they cannot explain that, oh, why am I a little bit good on some reactions, but a little bit bad on the other reaction, and how could it impact my final prediction on the materials? I don't know. I just let it fly. I have a simulation. I see something going on. Yeah. Should be fine. So that was till 2010. So now we can jump to the era of machine learning force field. That was the first generation of machine learning force field. It's still the idea, not that much different from the classical force field, where you start off from some kind of description of your system, either a pairwise description, or you build in a three-body having some angle, or even more sophisticated, you can put in spherical harmonics. And just on top of that, you just smash the MLP on top of it, or use Gaussian process. It was still a thing there. Just a little bit note on the literature, the first machine learning force field is actually very early. That was the first hype on the whole neural network, 1995. But unfortunately, they are too much before their time. Not much people cite their paper. And there was already active learning, and I think really changing the whole landscape of this community is the Bellapaniano and GAP. It really blew people's mind on how much you can do on force field RAM. And at that time, the parameter increase is not that much though. Bellapaniano, even though it's MLP, it's just 1,000 parameters for each two elements. Gaussian process is not even a parameterized model. At most, I think most of the software can handle probably 1,000 atomic state configurations. So the achievement of the first generation, of course, they are very crude or very early version of machine learning. They are able to do a lot of fancy stuff. So I was doing a lot of case study in my PhD during that time. I looked into this so-called dislocation structure. So you can see that the upper part, they have some regularity, they're cubic symmetry. Lower part also cubic symmetry, but in the middle, there is some irregularity. That's what we call defects in material science. This irregularity usually will just break the force field. The force field will not perform that well. But this kind of irregularity is crazily important for material science. For example, this is dislocation. They're very important for predicting mechanical properties. So before 1900, before people know the existence of dislocation, theoretical physicists always fail to predict how hard a material is. No matter how they approximate, it doesn't work. Only until a mathematician who propose, oh, how about you actually have some defects or irregularity that actually dominate the whole thing, even though it's just a very tiny core, about 1 angstrom, to, well, 1 to 2 lattice, that's 10 angstrom in the material, but it can dominate the whole thing, how they behave in mechanical shear string. And suddenly, our theoretical prediction gets right. But this is very hard for classical force field. I have to go to very expensive first principle method. And at that time, I was really impressed by what GAP can do. They go to like stacking force, dislocation, formation energy. They got all of them right. It was very impressive. And of course, as what theoretical physicists or computational people, they don't like each other's work. So they develop 100 different kinds of descriptor that you can build on. You can look into this review. It was a very good summary of what people have developed. The achievement at that time was a lot, right? You can describe some of the configurations precisely than what we cannot do before 2010. They already have a lot of methods that we're talking about this day. They have Bayesian method or ensemble method to predict uncertainty. They also have massive amount of data collection. Their data collection framework is actually way more sophisticated than what you see today. They go through phase diagram, many steps. Some of the workflow is like 30, 40 steps, while these days, most of the workflow is actually 2-3 steps. It's very brute force compared to that time. They're also starting to use modern optimizer. They are the founder of the machine learning force field. But they do have significant failure. First thing is generalizability. So as I showed previously in the table, you see an obvious triangle. So these columns are actually what they put in a training set, and the y-axis is what they test. If they haven't seen it, they cannot perform well on it. They cannot generalize the force field. It's still a little bit like classical force field that you need to throw. If you care about this material, throw more data on this material to your model. And then they also have no scalability to the number of element types, both Bella Perinello and GAP back to that time, like 2012 to 2015. They can only handle maybe binary or ternary materials that have 2 to 3 elements. The worst part is, at the time, they don't have open source code. People actually accept you announce success without open the source code for 5 to 10 years. Okay, no comment furthermore. Yeah. So then it comes a time, second generation force field, but let's go back to the equation because now there's more advanced machinery. So that's where we stop, right? We said because we apply a cutoff, pairwise interaction is not enough. We need to add many-body interaction. But then in modern architecture, right, from ResNet and all the more deep learning realm, we do have stacking. And then when you have stacking, you will talk about how you do your gathering in the graph. There are many mechanisms. So now we can start thinking of atom as a node in a GNN terminology. And all the edges, you can think them as just, or the bonds connected, you can think them as edges. Then because the constraint of the permutation invariant, we can only do certain type of gathering. So of course, the easiest one is the global gathering. You just sum all the nodes together or sum all the edge together. Then you do some operations, mesh some functional, some MLP on top of it, you're fine. But you can do slightly more sophisticated things if you're doing GNN, right? You can, for each atom, I gather around its neighbor. You can put on whatever in the variables. You can design very sophisticated gathering mechanism. That's how one method differ from, or one architecture different from the other architecture because people have different belief on which gathering is more effective. But this kind of gathering, we are very comfortable with that in force field, also because we have some constraint that I can talk with it. But maybe think it again, whether you want to use that in your generative model or whether you want to use GNN at all in your generative model. In force field, well, also one more terminology. Sometimes people ask me what's the difference between GNN and transformer. The answer is, if you're talking about graph transformer, they're exactly the same thing, because at the end of the day, you're just doing some gathering based on your neighbor list. So you can write a transformer into a GNN formalism, the message passing formalism. You have the atom sorry, I have a typo here, the neighbor, so it should be ij, right? And then you interact with the edges and take a softmax, that will be your message and your output. Or you can write in the transformer terminology QKV. It's just a notation. But of course, transformer is way larger than this type, and GNN is also way larger than the other type. You don't have to smash your transformer on top of graph. You can smash your transformer on something else. And also just give an example for people who always puzzled by all these box plot. Now should be slightly clearer when people draw a Z into it. It just, I want to have a way to define my node feature, and then there will be an attention layer that define how the interaction or gathering mechanism is. This particular one I'm showing is Graphomer. It was actually quite surprising at some point, because I know at the beginning, they were doing their positional embedding literally with the raw Cartesian coordinates without the distance, and it was really working. And my colleagues, so these are Microsoft in China, they told me that, oh, if you can stack to 1 billion parameters, why bother with invariance or equivariance? So it was very mind-blowing for me. It works, but it was just really horrible for molecular dynamic simulation, because you just can't meet the speed bar and many of the energy conservation. But if all you want to do is just smash the scoreboard, just, I have better MAE, yeah, it's true, you can get rid of most of things. And the one tiny thing that they add is, of course, the attention mechanism is slightly different because it's a graph. You do want to bake in a little bit more geometric information, so you add an edge bias into your attention model. Okay, so yeah, this part, as long as you have an interaction block, you can stack them. And obviously, there's a trend of changing between 2022. Before that, most of the people are only stacking 2 to 6 layers. Everyone is very cautious. But then after that, suddenly, people just go crazy, like, oh, let me stack 12 to 13 layers. And if people tell you equivariance is not scalable to large parameters, it's very likely that they just didn't do their normalization right. Almost most of the model, if you do your normalization right, is stackable, is scalable. You just need to be cautious, because you are harnessing very, very different beast between a small model of 1 million parameters to a big model that is a billion. The whole changing dynamics, everything has to change. So don't rush to draw your conclusion that you like invariant or equivariant, because it's a system engineering task here. Yeah. But when you do the stacking, be careful on what you do with your gathering mechanism or where you put your readout. Just remember what we have previously in a classical force field. For example, if all your readout is from the edges, you're falling a little bit like the Leonard-Jones potential at some point, that your total energy may scale with the number of edges. If you get all your readout from the node, then you behave a little bit like the solid state people. And of course, if you do the modern architecture, you map a lot normalization, many of this quantity may subtly different. So if you are doing training and seeing conflicting results on applying on data like OMO compared to applying to the data like materials project, if they behave differently, pay a bit attention. It's probably because the model is overfitting to one nature than the other, and the architecture design is not general enough. There's a reason that I said force field people like to use GNN and like to use cutoff. The exact reason is molecular dynamic people are just so harsh. They ask us to be able to model 1 million molecules. Sometimes I just can't squeeze my model into one single GPU. We have to constantly handle multi-GPU or multi-CPU communication problem. And if you look into these kind of parallelization mechanism, they will basically say, hey, I have a very large structure, I'll partition them into small cube and let each GPU see the small cube. And then inside the small cube, my GPU handle this, but because you can't just let things fall in the gap, right? You require a lot of continuity. So every GPU will actually have an overlap of information, these buffer zone. And then every time step when you evolve, you need to tell your neighbor GPU of what happened to the overlap region. They need to share information. They need to communicate. So that's why having a cutoff is very handy, because your network visibility is not going too far. But It can go super far if you have a very, very deep model. So basically, the buffer region or the information that you are gathering is the number of layer times your graph cutoff. So if you have a 30 layers model and 5 angstrom cutoff, you go through 150 angstrom. That's very large. Many of them MD simulation is just about that size. So you're basically forcing all the GPUs slowly communicating with each other, layer and layer. So as far as I know, some of the modern architecture or the SOTA model, if you try to do multi-GPU calculation, they can spend 20 to 30% of the time in cross-GPU communication. So you may rethink a little bit on how you design your message passing. There are 2 different ways of doing gathering. You can do gathering as the standard message passing, like you just talk to your neighbor, right? Take the J, but then the next message passing layer, J will inquiry their neighbor, you will get neighbor's neighbor, you will have several hop. And that's why the cross-GPU communication will also build up, because every layer you're inquiring more hops neighbor. You don't have to do that. You can also just do some local gathering method where you never see the node J information. You always only just see the HI and EIJ information. So this is what architecture like Allegro is doing. They're way more local. There's no cross-GPU communication, because when you have a full graph, you literally just partition them into all subgraph and let 4 different GPU handle it. You don't need communication. But there are very subtle things is if you do this, then the AB connection and BA connection is different. So some of the intermediates can be very confusing if you try to do that. Yeah, okay, so come to the golden part, equivariance. So now you manage to stack the model. But some people will tell you it's still not enough, right? Basically, I will show you later, up to step 4 is what people have done till 2019. From 2019, people realized if you're just stacking and only doing the pairwise information, all those normal stacking on graph network that borrow from other community, is not enough. You may want to introduce more information back. This is what they call the equivariance, right? Of course, your internal representation will rotate together with your input rotate, while invariance is your internal representation will not change if you rotate your input. I decided to pull out the equation because I feel like maybe it's easier to read the subscript here. So usually invariant, just the notation here, I will mark all the equivariance with the tilde. So they are a function of a vector instead of the function of a scalar. And then one way to build up your equivariant feature is just say, oh, if I have a radial part and the angular part, I can just put the angular part into spherical harmonic, and you can concatenate all the informations together. So then in this particular case, the equivariant feature, there will be each channel, each representation here, so each L, you will have 2 L plus 1. So this one is spherical harmonic. If you have L equals to 0, you have M equals to 0. L equals to 1, M ranges from -1 to 1. So you will have 3 features for L equals to 1, 5 features for L equals to 2, all the way up. If you decided to have all the L, then your feature will be L squared and then times the number of features. So this is an extra dimension compared to the invariant feature. So you're handling, for example, if your L equals to 4, then you have 16 more numbers to handle with when you're doing an equivariant operation. That's why sometimes people say equivariant is so hard, so heavy. And of course, because you want to preserve equivariant, right? Every time you introduce a new symmetry, the number of operators that you're allowed to use will be less. Like permutation, you can only do summation and plus, rotation and translational, or equivariant. Now you can only do, let's say I have this equivariant feature, then I can only do plus. Or if I want to do a multiplication of matrix on it, just note that you cannot put an M here. So you can only operate them all together for the same L. So then in this case, right, a 3-dimensional matrix interact with 2-dimensional matrix. There's a lot of things that you have to mess with in Torch. Also, like even the order of the index matter. If you have a very large matrix, think of how things store in the memory. You can't just arbitrarily swap the index. It will impact your performance and speed. And what's worse is the worst kind of interaction in this whole equivariant realm is they introduced the so-called tensor product. So if you want to have 2 equivariant features interact with each other but still preserve equivariance, is to say, okay, I have A and B tensor product to get a C here. Then you have to follow certain rules. So this is the original number that you get from A and B. So they are the L squared times the feature, right? C is the feature dimension. This is the number that you have. And suddenly have these Clebsch-Gordan coefficients. So it's a constant matrix that you have to live with in order to preserve equivariant. You cannot do a simple element-wise multiplication. All the multiplication that you have to do, you will blow up into a 3-matrix multiplication instead of 2-matrix multiplication. And if you look into dimension here, the original one is already L squared, and this coefficient is L to 6. Think of the memory, how they manage. They will probably store, if you just do a brute force INSUM, they will have a lot of intermediates. So basically, you first do the elemental-wise multiplication. It blow up the whole things with an extra L to 4. Like originally, it's already L to 2, right? 6 minus 2 equals 4. You blow the whole thing for the intermediate, and then you collapse them back again with the summation. And that's why everyone say equivariance is very slow, very expensive. It's exactly because you have to preserve the symmetry in this operation. And what's worse, some people are quite greedy. They not only want to preserve the equivariance, they also want to have a lot of things that are learnable, so they put some weight matrix here that are trainable. So think of the autograd. How many things that you need to cache behind in this operation? So immediately, from a standard invariant 2-matrix operation, now we are blowing up to a 4-matrix multiplication with indexing. It's really, really painful. I mean, luckily these days, NVIDIA, actually last year, they released a library to handle some of this. So if you want to walk around the engineering pain of writing an efficient torch algorithm or even CUDA code yourself, use their library. But even for their library, not every single operation is very fast. But for the most effective operation I know, like for example, they using this library increase the speed of the Maze MP for 7 times by just making this algorithm down all the level to the lower level coding, CUDA code. So you don't cache as much. You don't do some of the stupid indexing. There's actually a lot of engineering. So this is one of the classical message passing that people will pull out in the equivariant neural network, just to show you again. So for example, this one, it would be your input feature, HI, and then this one will be your edge, EIJ. So this constant is just representing that, oh, I'm actually doing a tensor product between these two, and that's your message, and sum over the message, you can get the output node feature. So there's nothing too different from an invariant graph neural network. It's just that you're doing all the operations on the equivariant landscape. But I do have an argument here, or I think many people in the old time have already say so, is the reason that we introduce equivariant is actually not for symmetry. The reason that we introduce equivariant is because when you do the thresholding, you throw a lot of information about the graph away. And we need to introduce the many-body effect back so you know the graph better and it's more effective. And also because in most of the modern architecture, we are only doing edge gathering. So that's essentially 2-body. So look into this. If I have a function, I have 3 objects, 0, 1, 2. They're interacting with each other, 3 vector, right? So in principle, the R1, RO1, RO2, you can derive the R12 in the function. So these two, which one is easier to retain the information that is inferring the R12? And then look into your gathering mechanism. Which gathering mechanism is easier to retain R12? So that's actually, I think, the major reason that people like equivariance, especially the false theorem, because it's just very effective for us to preserve the many-body information. It's very effective for us to preserve a lot of loss information due to the cutoff. And the reason that we have to use cutoff is because we may have periodic boundary, and we need to handle multi-GPU communication, and that's why we use cutoff. So step back. If you're doing a generative model on non-periodic structure, and you don't care about cross-GPU communication, and you already have full graph, think about it. I haven't do the testing myself. I'm just advocating, okay? You guys will pay the cost. Okay, so now we are ready for the second generation. So exactly, the second generation machine learning force field is just starting to introduce more this fancy descriptor or fancy interaction mechanism between the node and the edges. Here's an example from Nequip, so you can see it again. It's just a message here. Instead of just doing a simple multiplication, I'm doing tensor product. Well, the pioneer should really be Schnet at 2018. I think they're the first one that use a modern GNN architecture. They didn't use anything equivariant, so it was a little bit limited. But then later, people immediately starting to do equivariance. And then they all have this kind of box architecture. But at the end of the day, it's just talking about, I have a node information, I have some edge information, I want to gather them together with certain operation. The achievement at that time is, of course, to figure out most of the operator math and what will work and what will not work. Here is one proof that equivariant really work for force field. So basically, they see if you are only using invariant information, even though you grow your number of training data, the accuracy of the MAE is not improving. It will just saturate very, very fast and to a lower level. And for equivariant model, you need way less data, and it can converge to a much lower error or higher accuracy. And there are people that also saying, hey, if you keep improving your architecture, keep improving your descriptor, there is very good reward because you're pushing your trade-off between your speed and accuracy down further. So basically, every model, like every architecture, if you blow up the parameters, you always get slower. But at the same time, when you get slower, you are more accurate. But if you want to push things faster, so you just always live with this negative correlation trade-off. But again, one architecture is better than the architecture because they are living in different absolute number. So I think these numbers are still updating. This paper, they review it back to 2020. Still, many of them are generation 1 architecture. They also figure out that, well, second generation, that's the time that you're starting to see most of the database that is showing up, things like MD17, and QM9 or Open Catalyst Materials Project. And we're also starting to see the difference across the whole periodic table. If you actually zoom in the performance of your force field, even if you're trying to train a universal one or one-on-one, the limit that you can reach for different materials are very different. Some of the elements are just intrinsically more difficult than the other elements. For example, in this case, I think gold, you don't need that much high order of the equivariance. But then for things like, there should be an osmium, the L equals to all the way to 4 still improve. So the absolute white value is still improving the model accuracy. And yeah, and also there's a lot of muscle flexing already at that time. I'm not sure you guys know the ACM Golden Bell price. So it's basically a price that's set for whoever that can use the most amount of GPU effectively with a meaningful algorithm. The criteria is mostly on the number of GPU instead of whether the simulation itself is meaningful. And machine learning force field starting to get features like 2020 DeepMD. So that's a group from Princeton and also China. They literally just do bulk water and bulk copper, but they managed to blow it, I think it was 2,000 GPU, run it at the same time, and then if you prove that you don't waste too much time in communication, they managed to be the first one that make the award. Snap and Allegro were finalists in the later year. I didn't follow too much. Yeah, but I think every year there must be a force field group try to see whether they can just run a whole supercomputer to get effective billion or even trillion atom simulation with molecular dynamics. Of course, the first principle community is also catching up. I think later year, there's way more first principle, not force field. So it's the one that we get our training data on. They are also trying to push on this. The number of electrons, so here, if you roughly divide it by 20, they're just modeling 1,000 atoms. While the upper one, they're trying to model million to billion or even trillion atoms. Okay. But the challenge of this generation, of course, is they're very, very slow. Compared to classical force field, they're about 100 times slower. That's the kind of state. So classical force field usually can reach to 100 nanoseconds per day if you are doing protein simulation with GPU. But machine learning force field, most of the SOTA model these days, I think the best one is MTP, but at most 10 nanoseconds per day. And then it gets to today as the third generation. So you may see a lot of news on like UMA, ORB, Mace MP. I didn't list all of them. These are not history. This is currently ongoing that maybe some of us are already in it. But the starting point, it was, I would say it's 2019. So Chi is currently also working for Microsoft in the quantum company in US. When he published this paper back to 2019, everyone laughed at him. Nobody believed in universal force field. Like, nobody thinks that one thing can describe all. Unless you do the DFT or solve the Schrödinger equation, it cannot be general. You're just creating a problem yourself. But really, now it's what everyone is trying to do today, because we believe that if you scale your number of parameters at one day, you will be able to get very, very general. Yeah, so that's basically kind of how we come all the way to here today. But the later part of my talk, it's not going to be about architecture, it's about data. Data is actually way more important than architecture at this moment. Or let's say, just a few observations. I don't see any third generation force field have significant architecture improvement. Most of them are still using the architecture that were invented in the second generation. Let's say Maze, ESCN, Equiformer V2. Many of them did not change how things fundamentally should work. They're just blowing up the amount of data and blow up the amount of parameters. And of course, for every domain, if you're the first one come in, your investment of the return will be very high. The return will be exponential. And if you're late in the game, linear or even no return. So if you are more like a domain expert that's trying to use things and generate data, try to find something that nobody generate data on. So that's what our colleagues figure out. So these are, we always work in a massive team, but the lead scientists are at Shanghai. This is a model called MetaSim. It was, I think, first online already 2 years ago. So what we did is we figured out that most of the public data set, let's say Materials Project or Open Catalyst, most of them are live at ground state, 0 Kelvin. But if you are a material scientist working with real-world application, what we care about is high temperature, high pressure. If you look into a couple different kind of conditions, like for example, superconductor, they may live in very high pressure, or if you look into air astral, they are suffering high temperature. And the other example, for example, nuclear reactor, the core of the nuclear reactor is 600 Kelvin, 600 Celsius, and then some of the catalytic reaction happen at 200, 300 Celsius. There's nothing close to 0 Kelvin, or nothing close even to room temperature if you talk to a real material scientist. But there's barely any data with it. So what they do is just, hey, let's just brute force. Let's introduce way more data at different temperature and different pressure. So then they blow up the label of energy and forces with first principle, 17 million configuration and equivalent to 350 million. So I think this number has actually grown these days. We doubled the number of configurations, but it's not public. Yeah, but the architecture, as I say, they're using old architecture. If you're familiar with this terminology, MCGNet is not even having equivariance there. It's just invariant model. And Graphformer is, well, GMUM former is a mixture of invariant and equivariant. So they have most of the model, 90% of the weights load on invariant part, only the last 10% load on equivariant part. With all this new data, they find out at that time, at least, the model is performing much better than the other model that haven't seen this data on MedBench, even though MedBench at that time was mostly low temperature application. They also just removed the bias from Materials Project. Materials Project at the beginning was founded mostly for looking for materials for lithium battery. So it has a lot of oxides, but not other elements. So they increase or balance the in proportional distribution of all these elements in the periodic table. Then they find out, now because we have all this high temperature, high pressure data, we can also perform better at finite temperature and higher pressure. So in this case, they can successfully predict a phase transition of magnesium oxide, and it's pretty comparable to the experimental observation line in there.
Yeah, so they also try to compare formation-free energy. So this is actually very vital for experimentalists. Of course, there's a little bit problem here because most of the fossil is trained purely on DFT. So they compared to DFT, the model performs very well. But check in, check out, right? That's machine learning. If the DFT is not very accurate to experiment, we also may not be super accurate. So that's what we have to live with. Yeah, if you are richer, improving the data quality always help. But what they find is, maybe you don't need that much. Fine-tuning actually will be sufficient. You can just fine-tune with a higher accuracy data, then immediately, for example, this water, the prediction of the model, this is radial distribution, perform much better than a zero-shot out-of-box model. So I think this is still the convention these days. If you look into the model that are released literally 1 month ago, they are just still asking you if you have specific need, do a bit fine-tuning. We don't have things that work out of the box. You can also use it for active learning. I think for time's sake, I'll skip. But there's a lot of people rarely say how their model fail. But actually, if you apply your model to actual simulation, so this one, we are trying to do some Haber-Bosch reaction. So in the middle is a piece of iridium crystal nanoparticle. It's supposed to catalyze the reaction for Haber-Bosch. Is a chemical reaction for making fertilizer. They don't tell you what to do if the fossil goes wrong. Many people actually in the first generation of machine learning fossil, they already have the answer. They just tell you, hey, do active learning. But doing active learning with modern day model, it also gets harder. And also, especially if you are ambitious enough to go to gigantic system, doing active learning is even harder because, okay, if I encounter a configuration that is very, very wrong, like my fossil goes wrong, my uncertainty can already tell me to go wrong. But I cannot directly use DFT to relabel them because now I'm already entering million atom region. I can't do this. How could I do that appropriately? So what they did was, let's do a little bit cropping. But for computational chemists, they will know very well that cropping would not work out of the box. If I crop these atoms out of this continuum method, you immediately suffer from quantum effects. All the electronic states will be so different. When it's embedded in the materials, you may have metallic band, electron may be quite smear. Once you do the crop out, outside is vacuum, then you immediately confine the electrons around your atom. So then you have standalone molecular orbital instead of well-behaved, like band way of behavior for these electrons. Then what you relabel, actually, it will be massively different from what you want the model to learn. So what they did is do a little bit embedding, but optimize the embedding based on your uncertainty. So the idea is, if I put an embedding, I will fix the center configuration, which I don't know well, but then optimize the structure based on the uncertainty. So the outside embedding will actually be something that I know well, and usually something that the model know well is the low energy configuration. So in this case, they can just do active learning on a much massive data, on much larger molecular dynamic simulation that can give you more emergent behavior. So emerging behavior meaning if you simulate something like, let's say, 2 amino acid can never help you to understand how 100 amino acid folds, right? So this is emergent behavior. It also applies to materials. If you have more atoms, you will see way different. There may be green boundary, dislocation, or surface. The behavior is very different from what you can see from 10 atom crystal structure. Yeah, so with this kind of active learning, these are just numbers that they say the model behaved much better after adding this new active learning data. This is another visualization showing you that before the optimization, so the embedding will create configuration that is far away from what they have seen before. And then after the optimization, they push the configuration closer to what is seen before, but at the outer realm of the existing data. So you just gradually push out your knowledge area towards the unknown, but not that aggressive. And of course, because of this, they can do quite crazy simulations. I think this one, yeah, was a million atom simulation that they can do on the lithium phase transition, and they can match well with the experimental phase transition. And of course, the last example is what you see before, the Haber-Bosch reaction. So you can see, I think, the hydrogen was breaking, and then there was some hydrogen coming from the NH3 that they're reuniting and having the hydrogen out for the chemical reaction. So they can finally properly model this one. So this is before, and the top is after. So you only see some coarsening of the nanoparticle, which is like what you would expect, right? The real world is never that clean cut, like at 0 temperature. However, no matter how many data that you add, the data may conflict to each other. So if you look into all the database, they usually will report you how they label it in first principle, and you immediately get into the zoo of functional. Everyone is using different method. Of course, we're back to the Jacob's ladder. Everyone is at different distance to their heaven. They're not really reconcilable. Even though these days, many people tell you that, hey, you just do a multitask training, everyone have different head, and you will learn the geometry. We actually figure out that may not be the case. So this is a very tiny kind of theoretical proof that we try to do, is we really do a very well-controlled experiment to say, hey, I have exactly the same configurations and just different DFT label, and look into how effective if you do many, like multi-head training versus fine-tuning. The results was slightly disappointing. The left-hand side, you already probably seen this many times in different versions, is if you have pre-training data from lower fidelity, lower quality method, it always helps with your MAE. So without pre-training, the model, of course, learn with more data, but with pre-training, the cheap data, you just need a little bit of the high accuracy data to get pretty good. Of course, in the end, if you're very rich, they will cross over, but most of the time, like, you may live in log scale on the x-axis, so we're really talking about 10 to 1,000 different dollars difference. So pre-training really help. So to our disappointment was the multi-head does help, but it's not as much as fine-tuning. It's just kind of a way to get you exposed to many different geometries, like different data sets, some measure in molecules, some data set is catalyst interface, some data set is pure crystal. Yes, you can learn all the geometry, but the model, there's no magic for you to reconcile the difference from one label to another label. If you have exactly the same configurations with 2 different labels that give you 2 different energy, your model will just get confused. Yeah, so here's the summary. I don't know how much over time I am. Okay, yeah. So basically, we just go through the history on how things develop. I feel like we're seeing a circle now, like when we just develop one kind of formalism and people trying to develop more different kind of functional to fit it. And the next step is blow up the parameters. Once blowing up the parameters wouldn't help, they introduce a new formalism and more different formalism and keep blowing up the parameters. So maybe we're actually at the crossroad of a new formalism. Maybe one of you can do that. If you manage, let me know. Of course, the challenge is still there. None of the models these days have meet the bar from the domain expert who want to do, they can accept using 10 GPU, they're not that poor, but at least 1,000 atoms, 100 nanoseconds per day. And it needs to be general and accurate enough for all different sorts of systems. So this is the holy grail for a universal machine learning force field. And of course, there's still a lot of architecture challenge where we can talk about. There's data challenge, as I just said. Nobody managed to reconcile the data conflict so far. There's no magic. Sorry, you still have to do your fine-tuning if you have a particular system in mind. And at the end of the day, also just to remind ourselves, Laplace demon is impossible. So even if you meet the holy grail of the molecular dynamics simulation, you're not going to solve the whole multi-scale physics and chemistry. There's still a lot of framework bridging that we need to do to bridge from atomic scale to the real world. Yep. So I think that's it.
Any questions? So you mentioned CUDA equivariance, and there's also, of course, been open equivariance and reducing SO3 to SO2 and so on. Everything stuff that should enable doing like higher order with better scalability, right?
Yeah.
But then the question is, like, how high do we actually really need to go? Because it seems like we don't need the like over 10.
Yeah,
and so
over 10
on.
is too much.
But it's sort of one of the selling points of some of these papers, at least in the figures they have, right? So how much do we need in terms of the higher order?
So first correction on the number is many people actually only stop at L equals of 3 because they cannot afford L equals of 4. So let's not say 10, even 4 it will give you horrible memory bottleneck, right? 4 to 4, that's a lot. So far as I see, most of the elements, like if you look into one of the early paper by by this group, right? The things that need the most many-body interaction is heavy metal elements. So most of them, we find out maybe 5 to 6, you will already saturate. But for organic system, they are very light. I actually don't see the point of blowing up the L. Unless you're handling something that is very sensitive, you're not doing a force field, you're doing DFT functional, that kind of things is different story. Yeah.
I have one more question. So if we're learning energies, it's one thing, and if you're learning energies and forces, then we have 2 things we need to balance and add on stresses as well, it's 3. And it seems like part of balancing all these losses, it's sort of also a black arts.
It is a black art.
Coefficients, right? Like, is this just going to get more and more complicated the more things we try to learn in the same model?
I think so. You probably need to fall into something like curriculum learning, starting to see how you can do your scheduling cleverly. I haven't found a shortcut yet. You just have to see what works. Every model behaves very differently.
Thanks a lot.
Thank you for the talk. It was a great overview of force fields for someone who's never really truly encountered them before, so thanks. I have a question because when you were talking about the equivariance stuff, it seemed like it really does complicate a lot of things.
Yeah.
And you said it was a really interesting insight that the main thing that we bother with all of this is to preserve these many body features when you're doing the cutoff.
Yeah.
Right? But then, is there any other approaches to how you can do the cutoff so that you could sacrifice, let go of the equivariance? Is there a way to do a soft cutoff or something? Or is this a standard approach that everyone is just using the equivariance to preserve the features to then be able to do the cutoff?
So first is, many people are already kind of doing soft cutoff, or is already compulsory to do a soft cutoff because force field require continuity. So everything is mostly fading out. But if there's any other method to reintroduce the many-body interaction, I mean, of course you can do handcrafted many-body, so people do the 3-body interactions, like what I showed before, right? You do the gathering, you don't have to just do edge gathering, you can do way more complication. But at the end of the day, you are still sacrificing some of the, let me see, it was, where? This one, right? But then you do the for loop twice, then it gets more expensive. I think equivariance is very handy because once you figure out the math, you don't need to bother doing more handcrafted things, then your architecture comes very clean. But if you're, let me say it this way, if you don't do node center-based things, you may have more degree of freedoms to play with how you handle the many-body interaction. but I don't know the exact answer here. Yeah.
So thank you for your talk, and I would like to ask you two questions. First of all, do you think it will be possible for normal MD, classical MD user to use one time, like ML force fields?
Yeah, I think actually the other day poster, I already see someone using Maze for the liquid simulation, right? Is that person here? Yes, you can talk to her. She is actually using it.
Yeah, we talked, but
Oh.
as a, you know, I'm using classical MD in bulk. I'm simulating membranes, and I have 130,000 atoms.
Yeah.
Right. So will it be possible for me and my team one day to use, maybe?
I think these things is coming probably in a year. I see a lot of effort in making the force field a little bit much more lightweight, much more easy for multi-GPU communication. As I said, most of the universal force field that are released in the last at least 1 year, no people take care of the multi-GPU communication elegantly, and that's why they are really difficult for you to run the 1,300K atoms. But I think the problem probably will get solved within a year and a half. Just wait a little bit, and many people are now starting to aware and be very careful in how they interface with conventional users. So they will have all the things slowly getting ready, for example, using LAMPS or GROMACS or OpenMM if you are more familiar with those software. Yeah, I think it's a matter of time, but not now.
Yeah, okay. Thank you. And I would like to ask you about like more practical, like what is happening in that code. So when you are running simulation and you are updating like parameters for atoms during the simulations, right? With that.
So the
ML
parameters
software.
is always fixed. You're only doing the updating is always happen at your MD engine side, updating the position, and then you come back to the model, query the energy and forces, send it back to the engine, so that will be LAMPS, GROMACS, or OpenMM. It do the position update, and forward and backward.
Okay, so you're not kind of like changing these parameters which are fixed normally in MD.
So that is more falling into the realm of active learning, but these days active learning and the foundation model vibe is really conflicting with each other because foundation model is so big, training one may take 1 week or 2 with many GPU. So it's a bit hard or not that practical to do active learning like updating a model while running MD. You have to make some conscious choice.
Yeah. Okay, thank you very much.
Any more questions? Okay, let's thank our speaker for the very interesting talk.